focus my lecture on design aspects of battens. In last lecture, we have discussed different aspects of lacing systems, the general requirements, the codal provisions for design of lacing systems. Today, we will be focusing first on the design aspects and general requirements of the battening system. Then we will go through an workout example through which it will be clear how to analyze and design a batten plates. As we told earlier that batten plates are generally provided when the compressive load are only existing. That means only compressive load means axially compressive load is coming into picture, not the eccentricity. So when the load is acting concentrically, then we can use the batten plates. Of course, if eccentricity is there, then also we can provide batten plates, but extra care has to be taken. In practice, we generally use batten plates only when the axial force is present concentrically, not eccentrically. And batten plates means generally we use flat type of bars or rectangular type of bars as a tie, which is horizontal if the member is if the compression member is vertical. That means the batten plates are placed in such a way that batten plates and the main plate will be perpendicular to each other. Right. Now, apart from the rectangular bar flat type elements, we can use also I section, angle section or channel section as a batten plates, but for that also certain aspects has to be taken care. In practice, we generally use flat type bars as a batten plate. Now, first we will draw one batten plates with the main plates, main compressive member, and how it look like. We will see what are the terms, what are the parameters used for design. We will see, then it will be clear that what are the things we have to design. Like in case of batten plates, we have to see what is the dimension, that means thickness of the plate and the depth of the plate, what will be the spacing to each other, how many battens will be required. So all these things we will see step by step, right. So as I was telling that batten plates are generally used for axial load only. It consists of flat or plates. Angles, channels and I sections are also sometimes used as battens. It connects the components of the built up columns in two parallel planes. So how does it look? Let us see. Say suppose this is a section, elevation of the batten plate. Say here one plate is given, this is another one. So this is a plate, batten plate is here, another plate say suppose it is here. So this is the right, this is a plate, another plate is, so this is a compression member and this is another compression member, and tied together through this batten plate. So this is one batten plate and let's say these are the, if we consider the I section, so these are the centroid, means if we consider the I section is like this, say like this, right, and say this is the I section, right, and this is the web of the section, right. Now, so we can tell this as the spacing between two compression member, we can write as S, this is called S, right, and this is the plate, one batten plate we are providing here. Now this can be attached with the main plate in terms of rivet joint or in terms of welded joint or bolt joint. So as per the requirement of the site and as per the availability, we can make it as bolt joint or rivet joint or welded joint. We know the advantage and disadvantage of the riveted joint and bolt joint, and accordingly we will make, right. Now this is the plate, say this is called batten plate, this is the main member, compression member, right. Now this depth is called the overall depth, overall depth of the batten plate, which is written as D, and the outermost rivet distance is called the effective depth, D, and spacing will be middle of this plate, spacing of the batten when it is told. So middle of this plate and middle of this plate, CG, distance of between two, this is called spacing, which is denoted as C, right, and the distance between two inner riveted group is denoted as A, distance between two inner groups. So from here to here, this is called A, right. Now so this I can say as a spacing between two compression member. Here I section has been used, so accordingly it has been made. Now here another important point will come later, that if this is y axis and if this is x, then we have to see that ry should not be less than rx, that also we have to check, and generally we use that ry is equal to rx to get the maximum efficiency of the system. So what we are seeing here, that batten plates will be something like this, where this is, in fact this is called C, the spacing, and this is the S, and this distance is called A, this distance, rivet to rivet distance, this distance is called A, and we have to see that ry should not be less than rx, right. So these are the things we have to remember. So what we are doing basically for design of battening, that means we have to decide this C, spacing of the battening, then this D, total thickness, that means overall thickness of the batten, and then depth of the batten, and then thickness T of the batten, right. So these three things are important, D, T and C, spacing, and then attachment to the main plate. That means we have the main plate of this and we have to attach this batten. So how many number of rivets will be required, what will be the configuration of the rivet, that we have to decide, or what will be the welding length, how much weld length is required. So that also we have to decide, weld depth or weld thickness, throat thickness, those things we have to decide if we are going for the connection as welding connection, right. So these are the things we have to decide. Now in last lectures, in last 2-3 lectures, we have seen how to design a built up section, and after designing a built up section we have to make the lacing systems or battening system. We have to design the lacing system or battening system, and how we have done we have seen. Now here also in a similar process, first we will see what are the general requirements, then we will see what are the codal provisions, what code are specifying. So once we know the general requirements and codal provisions, then we can design the system as per the codal provisions, right. So in today's lecture I will try to finish all the things, that means shortly I will discuss the codal provisions, which is not much because it is almost similar to the lacing system. Then before that the general requirements, then I will go through one example, workout example, how to design a battening system, right. So, let us see. So, first we will discuss about the general requirements. General requirements is in clause 5.8.1 of IS 800/1984 it is given. In fact, in clause 5.8 of IS 800/1984 the details requirement of battening system has been given, and in 5.8.1 the general requirements have been given, and then the design aspects has been given, then the end connections have been given. So, if we see the first para, that clause 5.8.1.1, what it is telling, let us see. It tells that compression members composed of two main components, Batten should preferably have their two main components of the same cross section, right, and symmetrically disposed about their x axis. So, the main component members should preferably be symmetric. Where practicable, the compression members should have a radius of gyration about the axis perpendicular to the plane of the batten, not less than the radius of gyration about the axis in the plane of batten. That means Ry should preferably be greater than Rx. So, these things has to preferably maintain. This is the codal provision in 5.8.1.1 it is telling. Then in 5.8.1.3 it tells that the battens shall be placed opposite each other at each end of the member, and points where the member is stayed in its length and shall as far as practicable be spaced and proportioned uniformly throughout. So, this is written in the code, you can go through the codal provisions, then you will understand in better way. The number of battens shall be such that the member is divided into not less than 3 bays within its actual length from center to center of connection. So, at least 3 bays should be there, right. So, we do not, in fact, we do not have to remember all these provisions. While designing, we can have a look of the codal provisions in clause 5.8.1 and 5.8.2 and 5.8.3 before going to start the designing. So, we do not have to remember, we can just have a look, we can read that one and we can understand from there, right. Next is the design requirements, which is given in clause 5.8.2. 5.8.2 of IS 800/1984. In clause 5.8.2.1, the details about forces coming into batten has been described. What are the forces will come into batten, that has been told, and according to that we have to check whether that much force exerted on the batten can be taken by the batten or not. The force which are coming to the batten from the axial compression member is able to carried by the battening plate or not, that we have to check. So, first we will see what are the forces are coming, then what are the stresses due to that force is coming, whether the stresses is exceeding the permissible stresses or not, that we will see and we will check accordingly, right. So, in batten also the code has suggested that this shall be designed to carry bending moment and shear arising from transverse shear force V of 2.5% of the total axial force on the whole compression member. So, like lacing system, the transverse shear will come 2.5% of the axial compression. Transverse shear will come 2.5% of the total compression member. So, V will become 2.5% of P, where P is the axial force on the compression member. P is the axial force on the compression member. So, the transverse shear we can find out from this codal provision, that V is equal to 2.5% of P, where P is the compression force. in the compression member. So from this we can find out the transverse shear force. Then what we will do? Then we will find out the longitudinal shear and moment. Right? The batten shall be able to resist simultaneously a longitudinal shear of V1 is equal to Vc by Ns and moment of M is equal to Vc by 2N. This much shear and moment has to be carried by the batten. This is told in clause 5.8.2.1. So as we know V which is the transverse shear force, which is 2.5% of the compression force P. So we can find out the V1 and M, where C is, as we know, C we can write, in fact this is C, minimum transverse distance between center of gravity of rivet grooves or welding. Sorry, C has been given here, this is S. Sorry, C is center to center distance of battens longitudinally. In fact, if we see the picture, we will be understanding. This is called C. C is this much. This is C, right? So as we know, the center to center distance of battens longitudinally, so we can find out the value of C. And N is number of parallel planes of batten. Number of parallel planes, that means when two members are there, then we have a batten here, and in opposite direction also another batten is there generally. That means if we have a I section here and if we have a I section here, we generally used to tie by this batten. So number of batten plates are 2, right? So here N will become number of parallel planes of batten, that will become in general 2, right? Another thing is S. S is, this is S. S is the minimum transverse distance between center of gravity of rivet grooves or welding. That means which one? If we see the picture, center of gravity distance of rivet or welding. This is called S, right? So S we can find out from here. In this way, we can find out the value of B1 and M, longitudinal shear and moment, right? So forces in terms of longitudinal shear and moment can be calculated from the codal provision, where code specifies that the transverse shear developed in the batten will be the 2.5% of the compressive force acting on the main member. So from this we can find out the transverse shear force V, then we can find out the longitudinal shear V1, which is called Vc by Ns, and the moment M as Vc by 2N, where C and N and S are given here. Then we will check for longitudinal shear stress and check for bending stress. Now we know the longitudinal shear force V1 is means we have calculated. So the stress we can find out, tau is equal to say V1 by D into T, which is called longitudinal shear stress. So longitudinal shear stress tau will become V1 by D into T, where D is the depth of the batten. If I see, this is, say this is one and this is another member connected with the batten. Now, so this is D of the batten and thickness T, right? So longitudinal shear stress tau will become V1 by D into T, where D is overall depth of the batten and T is the thickness of the batten, right? And this should not be greater than tau Va. Tau Va is permissible average shear stress. Tau Va is the average shear stress, permissible average shear stress, which is given in the code, right? In case of power driven shop rivet, we used to consider the permissible shear stress tau Va as 100 MPa, right? And similarly, we will check for bending stress. Bending stress means we know the bending moment whatever it is developing. Now bending stress we can find out sigma b is equal to m by z, and m we have found already, and z is nothing but the section modulus, which will become 1 by 6 d into t square, right. Now this, if I see, sorry, this will be d square into t, 1 by 6 d square into t. This should be less than sigma bc or sigma bt, where sigma bc and sigma bt are the permissible bending stress in compression and tension respectively. Permissible bending stress in compression and tension respectively, and this value are given in the code, which is for FY 250 it becomes 165 MPa. Sigma bt or sigma bc, the permissible bending stress in compression and in tension, are generally taken as 0.66 Fy. So from this value is coming around 165 MPa for Fe 250, means if Fy is 250, means 250 grade of steel, right. So in this way we can check the longitudinal shear stress and bending stress. So if it is okay, then the assumed dimension of the batten, that means d and t, is fine. If it is not okay, then we have to increase either d or t suitably. Next we will find out the other things like effective length, because we have to find out the permissible compressive stress in the main member. Then again we have to find out the radius of gyration of the main member for checking and for getting the spacing c between two battens, right. Now in table 5.2 the effective length has been given, table 5.2 of IS 800. In that note, in the table at the below, one note is given where it is told that the effective length of the column is increased by 10% to get the design effective length on the case of the batten. So in case of batten, the effective length of the column will become 1.1 LE. Okay, this design LE will become 1.1, 10% increased. The effective length whatever we are going to calculate, that will increase by 10% if this is used for batten, for calculation of batten forces and other things, designing things. We will calculate the effective length as 10% more than the actual effective length, right. This is given in table 5.2 of IS 800 1984 in the note, right. And in clause 5.8.2.3 the thickness of batten has been defined. The thickness of batten has to be 1/50th of the distance between the innermost connecting rivets or weld. What it is told exactly? That the thickness of the batten T or the tie plates should not be less than 1/50th of the distance between the innermost connecting rivets or welds. Innermost connecting rivets or welds. So in this way we have to decide the thickness T. So T will be, minimum thickness T will be AI by 50, where AI is the distance between the innermost connecting lines of rivets or welds. That means, as we understand that suppose this is a I section and this is another I section which are connected each other through batten plates. Means if we have connected through batten plates, if I see the plan, now this is the rivet line, this is called gauge distance, this is called gauge distance, right. This is the rivet line. Now this distance is called A, right. So A by 50, minimum thickness of the batten should be greater than A by 50, right. Now So, in this way you can decide the thickness of the batten. Another thing is depth of the batten. As per this clause, it told that the effective depth of battens D shall be taken as distance between end rivets or end wells, as follows: as distance between end rivets and or end wells. So, this D should become greater than 0.75 A for intermediate battens. So, the effective depth of the batten should become more than 0.75 A, where A we have already told, this is A, the distance between the innermost connecting lines of rivets or wells, right. So, D we can find out as 0.75 A for intermediate battens, and for end batten this should become, D should become greater than A for end battens. Okay. So, in general end battens depth will be little greater than the intermediate battens. This is as per the Codal provision is given, and in any case always it should become greater than 2B, where B is the width of the main plate. This is wave width, flange width. This is called B. So, D, the thickness of the batten should be greater than 2B. Okay. So, D is the effective depth of the batten, A is the centroid distance of members, and B is the width of member in plane of batten. Okay. So, in this way we can decide the depth of the batten. Then another remaining part is spacing. Spacing means if two plates are connected through batten, so suppose like this it is connected. So, suppose one batten is here, another batten is here. Now, spacing will be this one, means middle to middle, this C. This is one batten, this is another batten. Okay. So, in this is defined in clause 5.8.3 of IS 800 1984. What is it told? That the spacing of the batten C be such that the slenderness ratio of the lesser main component over the distance is not greater than 50 or 0.7 times the slenderness ratio of the main member as a whole about the axis parallel to the batten. That means, C by RC minimum should become less than 50 or 0.7 times the lambda, where lambda is the slenderness ratio of the main member as a whole about the axis parallel to the batten, right. So, this is the condition from which I can find out the value of C, the spacing between two batten, right. So, as per the clause 5.8.3 we have to find out the spacing between two battens, that is can be decided from this equation, which is called C by RC minimum is less than 50 or C by RC minimum is less than 0.7 lambda, whichever is lesser, right. So, from this we have to find out. Then is the end connections. End connections means battens are connected to the main plate, the compression member. So, these battens either we have to connect through welded joint or through rivet or bolted joints. So, as per the designer's choice, here or she has to choose any type of joint, and accordingly he has to find out the configuration of the connections, right. In case of riveted joint, what we will do? Riveted joint, we know the force what is coming. So, for a particular diameter of rivet, we know what will be the rivet value. What will be the rivet value for a particular diameter of rivet and the thickness of the batten, we can find out the rivet value. In generally, rivet value can be find out from single shear and from bearing of the plate. Then the lesser one will be the rivet value. Then we can find out what is the means if the number of rivets is decided, then what is the force coming to that. Then also we know the CG of the rivet, we can find out from the configuration, and then we have to find out what is the forces coming due to the eccentricity, due to the moment, right. Then we have to find out the resultant of the forces coming from the axial directly and from the moment, right. And then once we find out the total forces coming due to moment and the axial force, means direct force, then we have to see whether it is becoming, the resultant is becoming more than the rivet value or not. If it is becoming more than the rivet value, then we have to redesign, we have to increase the number of rivet or we have to increase the dimension. Otherwise, if it is less than the rivet value, then it is okay. The assumed configuration is fine to carry that much load. In this way, the rivet joint can be done. In case of welding joint, certain parameters, means certain guidelines have been given by the code which has to be taken care. This I am discussing. This is given in clause 5.8.4. In clause 5.8.4 of IS 800/1984, this is given. What it is told, that design the end connections to resist longitudinal shear force V1 and the moment M as calculated in earlier step. So, we will design the end connection in terms of V1 and M, which already we have calculated. Then what we will do, what are the things guided by the code, that is the for welded connection lap should be greater than 40. What is lap length? I am coming. Lap should be greater than 40. Another thing is total length of weld at edge of batten should be greater than d/2, where d is the overall depth of the batten plates. Then length of weld at each edge of batten should be less than 1/3 of total length of weld required. It should be less than 1/3 of total length of weld required. And return weld along transverse axis of column should be less than 40. This is also important. So, these are the criteria, guidelines which is provided by the code in clause 5.8.4 of IS 800/1984. So, through this guideline we have to design the weld connections. That means, how do we do the design the weld connection? First we have to see what are the forces are coming, then we have to see what are the length of weld and depth of or thickness of the weld is required, we will calculate, then we will distribute the weld in such a way that these are maintaining these codal provisions, right. So, in this way we can design. Now, I will give the details of this in the diagram, so that we can understand what are lap and what other things are telling by the code. So, this is one main member, this is the batten plates, another main member here, so these two main compression member are tied together through the batten plate. This is batten plate. Now, this has been welded. Now, this is the overall depth of the batten plate and thickness is D, thickness of the batten plate. Now, welding has been done, say in this way. First we have to decide what are the total length required for welding with a particular thickness of the weld. Then we have to distribute properly, so that the codal provisions are maintained as well as the total lengths are also maintained. So, this is, if I say A, this should not be greater than, means less than d/6. That means, this should be greater than at least d/6, where d is the overall depth. of the batten plate, and this is called B, and this is, say again C. If we say, this also should not be less than d by 6, and this is the, this we can say suppose C dash, this should not be less than 40, right, and say this is the, in our case we are using channel section, we can find out the diagram accordingly. This will be the diagram, and if we see the plan, it will be something like this. It is not to scale, just here. If we use channel section, then this will like this, right. So these are the channel section. Okay, welding has been done like this. Now here condition is that A plus B plus C, that means this plus this plus this, this should not be less than d by 2. This is one, right, and other things are, I told that A should not be less than d by 6 and C should not be less than d by 6 and C dash should not be less than 40, where T is the thickness of the plate, T is the thickness. Okay. So this codal provisions has to maintain. So whatever I am telling here, I am writing, means I am, diagram is given here. So what we told here, that you see, for welded connection lap should be greater than 40, that means lap should be greater than 40, that means it should not be less than 40. Okay, C dash. Then another thing is that the total length of weld at edge of batten should be greater than d by 2. So total length of weld at the edge, A plus B plus C total length, this is the total length, it should be greater than d by 2. Okay, and A and C, the end return should be at least d by 6, that also has to be maintained. Okay. So with this codal provisions, we have to design the weld connection for the batten plate. So whatever we have seen in case of design of batten plates, that certain general requirements are there which we have to follow, and certain guidelines for design of batten plates are there in the codal provisions. Guidelines means what should be the minimum thickness of the batten plate, what should be the minimum depth of the batten plate, and what should be the minimum spacing of the batten plate, that has been given in the code. Maximum spacing of the batten plate. Okay. So from the codal provisions we can find out these three: thickness of the batten plate, depth of the batten plate, and the spacing of the batten plate. Then other things are that we have to check the longitudinal shear stress whatever developing in the batten plate, and the stress due to bending we have to check, and we have to check whether the developed stresses are less than the allowable stress or not. If it is less than the permissible stresses, then it is fine, otherwise we have to redesign. Redesign means we have to increase the dimension of the batten plate in terms of either thickness or in terms of either depth. Then what we will do? Then we will go for end connections. End connections means either we will do the connection between batten and the main plate with the riveted joint or bolted joint or welding joint. So in case of riveted joint, we know what are the loads are coming and what is the diameter of the rivet. So accordingly we can find out the configuration of the rivets. That means where the rivet should be placed, how many rivets should be placed, and what should be the capacity of the rivet group, we can find out. And if we go for welding joint, then we have to see what will be the length of weld is required for the forces coming into picture. Then we have to maintain the codal provisions that what will be the distribution of the welding length and return weld, lap length, all these things we have to decide as per the coded provisions, and we have to see whether we are maintaining or not. So, in this way we can design. Now, we will go through one example through which we will be able to clear how to design a Batten plates. So, this example has been worked out in previous lecture, that a built up compression member having effective length of 6 meter and carrying an axial compressive load of 1000 kilonewton. Design the member using battens. In last workout example, we have done same thing using lacing plates. So, here what we are seeing, that effective length is 6 meter and the compressive load which is carrying by the member is 1000 kilonewton, and actually this example is same as done in case of design of lacing member. So, we will do the same thing for the Batten member. The advantage of doing the same problem is we can see the difference, what are the different things are coming in case of battening with respect to lacing systems. And the first step, that means the design of built up sections, we do not need to reiterate again, because we have done in the last class. So, we can have a look there, right. So, in last class what we have seen, for this effective length and the load, we need to provide 2 ISMC 300 at 35.8 kg per meter back to back with a spacing of 183 millimeter. That means 2 ISMC we are going to provide with a spacing of 183 millimeter. This we have calculated in last lecture, right. In last lecture, up to the calculation of built up section, means finding out the built up section and the spacing is common for this problem also. So, we are not going into details that. Then there we have done design of lacing using single system and double system, double lacing system, single lacing system. Here we will do the things using batten, right. So, let us see how to do it. So, first let us draw the things which we got in earlier design, and then we can go the details of the battening. Suppose these are the battening. These are another plate. So, this is a channel section, this is another one. This I am drawing because from this configuration we need many dimensions in our calculation of the batten plates, right. So, what are the things we know already? That is, this we know, the spacing, clear spacing is 183 millimeter, and we know the, this is the wave, right. Now, another thing is we know the rivet group, as per from the SP6 we can find out the gauge distance, this is called G. This is given as 50 in code. If we see in SP6 we will see G is given as 50 millimeter, right. So, if we provide the rivet here, right, if we provide the rivet in this, then we can see this distance also we can find out. That means this distance, right. So, this distance will be 183 plus 2 into 50, that means 283 millimeter. So, this distance also we have, right. and this channel sections we have IS MC 300, right. Channel section we have chosen IS MC 300 with the back to back and 183 mm spacing. So these things are already calculated in last lecture. Now we have to find out what is the depth, overall depth. This we have to find out. What is the thickness? This we have to find out. What is the number of rivet, number and diameter of rivet, that also we have to find out, and the C we have to find out, the spacing. So these are the things we have to find out, right. So let us see step by step how to find out all this unknown. So these 4 unknowns are there. So when we are going for design of batten, means first we will go for design of the built up section, which is common and which is done in earlier class. Now we will go for design of batten. In step 1 we will first find out the spacing of the batten, spacing C. So as per the codal provisions, C should, means this expression should be maintained, that C by RC minimum should be less than 50 or 0.7 times lambda, whichever is less. So first we can see C should be less than 0.7 lambda into RC minimum, 0.7 lambda into RC minimum, that means 0.7 lambda into RC minimum. RC minimum is given in the code, means for this configuration what is the RC minimum we can find out, which has find out in last class, that is 26.1 millimeter. Another thing is lambda. Lambda is also find out in last class. Okay. Only thing is, what is lambda? Lambda is L by R. Now as per the codal provision in table 5.2, it is told that length will be increased by 10%. Length of the compression member, effective length of the compression member will increase by 10% for the case of batten. So here lambda will be going to increase by 10%. So I am multiplying 1.1 with the earlier one, 58.8. So this will become 1.1 into 50. So if we calculate this, the C value is coming 1020.93 millimeter, 120.93 millimeter. So the spacing between two batten is coming from one expression, that is 1020.93 millimeter. Another is, or C should be less than 50 into RC minimum. So 50 into RC minimum, that is coming 1305 millimeter, 1305 millimeter. So these are the two. So C should become lesser of these two at least. So now let us provide spacing C as say 900 millimeter. Let us see, because this, the spacing of two battens should be less than these two. So we are say providing say 900 millimeter, right. Then what will do? Then is thickness of batten. So C first is defined. So C is now known, that is 900 millimeter. Okay. Now it is known. Next we will find out the thickness of batten. Step 2 we will try to find out thickness of the batten. Now thickness of the batten, we know that this should become A by 50, means minimum thickness should be at least A by 50. Okay. So what is A? A we know, we have calculated, this is the A value. Okay. So A we are finding out, because gauge distance is given 50, so A will become 2G plus S. So 2 into G is 50 plus S is 183. So this is becoming 283 millimeter. Thus the A is becoming 283 millimeter. So we can find out the minimum thickness as 283 by 50, which is coming 5.66 millimeter. So the minimum thickness we are also getting. However, we see as a provision against corrosion, minimum a thickness of 6 millimeter should be provided. So in any case, if it is coming less than 6 also, we have to provide at least 6 mm from the corrosion point of view, right. So, minimum thickness we are going to adopt 6 mm. Suppose it is becoming say 3, then also we have to consider at least 6 mm, right, or more than that. So, let us see with the minimum thickness 6 mm. So, let us decide the thickness as 6 mm. So, what else we need? We need to know the D, depth of the batten plate, right. So, step 3 will become depth of batten. Okay. So, depth of batten, as we know, A is basically 283 millimeter, which we have calculated. So, from the codal provisions we know for intermediate batten D should become less than, means at least greater than 3/4 of the A. So, if we put the value of A as 283, then D will become 3/4 of 283, which is becoming 212.25 millimeter, right. So, D has to become 212.25 millimeter. Again, for any batten D should become at least 2B, where B is given 100 mm, means for ISMC 300 we know this is B, which is given in SP 6 as 100. From code we can find out the dimension of this. So, B is given, so here at least 200, D should be greater than 200 and 212. So, from these two we can provide a minimum depth of say 250 millimeter. The effective depth as 250 millimeter we can provide. Okay. And if we use 20 mm diameter of rivet and edge distance of 40 mm, then the overall depth will become 250 plus say edge distance is 40, so 2 into 40. So, this will become 250 plus 2 into 40 is equal to 330 millimeter. So, the overall depth we are going to find out as 330 millimeter, because we are assuming the effective depth as 250 millimeter and the edge distance as 40 millimeter. So, we can find out as 330 millimeter. Next, we can find out the stresses. So, we are going to provide, this is the thing, that 330 by 6 mm batten plates at a 900 mm center to center. So, this is the outcome we got, right. So, here D we are going to decide 330 mm. So, all the things we found, thickness, depth and spacing. Now, we have to find out number, and before that we have to check the stresses. Okay. So, in step 4 we will check the stresses due to longitudinal shear and moment. So, we can find out first transverse shear V is equal to 2.5% of the total load, this is P. So, this is becoming 25 kilonewton, 2.5% of 1000 kilonewton, right. So, 25 kilonewton. Now, moment in batten plates due to transverse shear we can find out from the formula M is equal to Vc by 2N. So, V is 25 and C is 900 millimeter, that means 0.9 meter, and 2 into N is the total number of parallel planes, that is 2. So, if we calculate we will get 5.625 kilonewton meter. So, moment we are getting. Next we are getting the longitudinal shear V1, this will become Vc by Ns. So, V is 25, C is 900 mm and N is 2 and S is spacing, that is 283 millimeter. So, from that we can find out the longitudinal shear V1 as 39.75 kilonewton. So, longitudinal shear stress also we can find out, which will become V1 by dt. Now, if we put the value of V1 and D and T, we will get the value as 20.08 Newton per millimeter square, which is less than tau Va. In this case, tau Va is 100 Newton per millimeter square. For the steel, as we are using Fy 250 with, okay. So, tau Va is 100 Newton per millimeter square. That is why longitudinal shear stress whatever coming as 20 is less than tau Va, so it is okay. Similarly, the bending stress in batten due to transverse shear can be find out, that is sigma b is equal to 6m by t into d square. 6 moment is this one and t is 6 mm and d is 330. Okay. So, from this I am going to get as 51.65 Newton per millimeter square, which is less than sigma bt or sigma bc, which is 165 Newton per millimeter square. So, from this we can find out that this is also okay. So, from stress point of view, these are quite okay. This also we can make. Next, what we will do? Now, we will go for design of end connections. So, in case of end connections, if we use 20 mm power driven shop rivet, then in single shear the rivet value will become tau Vf into pi by 4 d square, tau Vf into pi by 4 into d square, where d is the gross diameter 21.5. So, this is coming 36.3 kilonewton, and in bearing this will be sigma Pf into d into t. So, if I put the value sigma Pf as 300, d is 21.5 and t is the thickness 6. So, this is coming 38.7. Hence, the rivet value will become lesser of these two, that is 36.3 kilonewton. So, rivet value also we are going to get. Next, what we will do? Next, direct force on each rivet, right. So, for that we have to start with some number of rivets. Say, let us provide 4 rivets at 80 mm center to center distance, 4 rivets at 80 mm center to center distance. So, direct force on each rivet we can find out, because 4 rivets are there. So, Fa will become R by 4, where R is we found earlier R, right, longitudinal shear 39.75. So, R by 4, this is coming 9.44 kilonewton. So, direct force on each rivet is coming 9.44 kilonewton. Similarly, force due to moment on end rivet, that will be becoming mr by summation r square. So, now if we provide 4 rivets, says this is the Batten plate, say 1, 2, 3, 4 now, right, and this distance has been taken say 80 mm, and so this is 40 and then again this is 40. So, this is the way, sorry, this will become 45. Okay, we will calculate this one, yeah, 45. Okay. So, we have to find out the distance of extreme rivet, that will become 40 plus 80. Okay. So, m into r, this is the r, this extreme distance of extreme rivet, by summation r square, 2 rivets in each side. So, 2 into 40 square plus 2 into 40 plus 80 whole square. So, this will become 21.09 kilonewton. This can be rather Fm, force due to moment. Okay. So, 21.09 kilonewton. Hence, resultant force at end rivets will become, so Fr will become root over Fm square plus Fa square. So, the resultant is coming 23.11 kilonewton, which is less than the rivet value. Rivet value was calculated as 36.3 kilonewton. So, the resultant force is coming less than the rivet value. So, it is okay. So, the design is okay. So, we can use that 4 number of 20 mm diameter of rivets at 80 mm center to center distance and with an edge distance of 45 millimeter, that we calculated, because total depth is 330 minus 3 into 80 is equal to 45. So, we are going to get 45 mm. So, if we see now the details of the design, we will see that here number is 4 numbers of 25 rivets, 25 diameter of power driven shop rivets, and 4 numbers means, say suppose this 4 let us provide, and this rivet distance will become 80 and this edge distance will become, this will become 45, right. So, in this way we are going to get all the details. So, with this I like to conclude the today's lecture as well as the chapter of compression member. In next class we will start a new chapter. Thank you very much.